Hello students, today we're going to be looking at what mathematicians mean by proof, basically the standard of certainty. So let's start out today's video with a deceptively basic question. How do you actually know with absolute certainty that 2 plus 2 is actually 4? And if you ask anyone on the street, how do you know this? They're going to be looking at you like you've completely lost your mind. And obviously, they'll say something like, "Oh, look at your fingers, right? Are you stupid? 1, 2, 3, 4, right?" Or because my elementary school teacher told me so, or it's just completely obvious. But as we venture into higher mathematics and try to understand the very fabric of infinite spaces, relying on what feels obvious is a massive trap. So, in everyday life, an intuitive guess is usually good enough to get by, but in real analysis, we don't care about what feels true. We care exclusively about what we can logically guarantee to be true with zero exceptions across the entire universe. So, the start of this course is going to be exposing to a lot of these axioms and theorems that seem very obvious and intuitive, but you're going to be realizing that it's very hard to actually prove what these are and why these are true. So let's think of a mathematical proof like building a, I guess, let me think, an unshakable brick wall, right? You start with a few foundational facts that are completely undisputed and accepted as starting points, and we call these axioms. So, undisputed, and then there are starting points. And these are what form your solid, unmovable bottom row of bricks. And to add a new row of bricks on top, every single new brick must fit perfectly and lock tightly into the row directly beneath it using absolutely flawless deductive logic. And if there's even a tiny bit of wiggle room for assumptions or single gap in any step of reasoning, the stability of the entire wall is compromised. So it's a very strict process. A proof is simply step by step demonstration, right? A linear demonstration showing your new claim uh, fits perfectly with the facts and is into facts we already know, right? So then new claim with the facts, we get something that's true, right? So there's no guessing, no hand waving, and no leaps of faith allowed. So why are mathematicians so unbelievably strict, right? It's not because they're trying to be difficult, academic, or pedantic, right? It may seem like that. It's because they know human intuition is incredibly easy to fool, and that's what ultimately led to this issue in logic when we started pushing calculus without actually really knowing the very essence of, numbers. So let's look at another, I guess, classic example. We're going to be looking at, I guess, let's just write it first. Say this, right? 0.9999, and it just repeats infinitely. So it just goes on forever, right? When you first see this, your gut may shout, right? Like, um, I guess like it goes on forever, but it doesn't seem like it's exactly one, right? But because this goes on infinitely, this is precisely equal to the whole number one. And obviously, when you're first trying to wrap your minds around that, right? It seems like it is a flaw, right? Because there's a tiny microscopic fraction that's less than one that is making this not equal to one. So we can, but logically, we use a proof to demonstrate that these are the exact same number. When our feelings fight against pure deductive logic, our feelings lose every time. So proofs are the essential safety rails that protect us from being deceived by these appearances. So, I guess to reiterate, right? Proof is the mathematician's ultimate answer to doubt. It transforms an intuitive guess into absolute knowledge absolute, undeniable knowledge that will remain true forever. And just like a builder using completely different tools to build different parts of a house, mathematicians have developed three, I guess. We'll start out with three. Timeless strategies to build their proofs, which include direct arguments, uh, the contrapositive flips or inversions, and the contradiction trap strategies. So in our next video, we're going to be breaking down this logical toolkit and look at examples of how each one of these works and learn how to choose the perfect weapon for any mathematical challenge. So see you in the next video, which is going to be direct versus contradiction versus the contrapositive proof. Thank you for watching, and I'll see you next time.